Alright, good morning. Welcome to my stream. What we did, just a brief recap of what we did yesterday, was to add the objects, the operators for the binary, what's-its, which I don't have here. Thought I had that. Oh yeah, we added a bunch of tests for various things and git log. Yeah. So we did operators, we added tests and runtime errors. Something else we did was refactor the object stuff so that we don't have a separate true and false, but we have a bool, just like we have strings and numbers. So that's all good. What we're going to do today, actually, so one of the things that we failed to do yesterday was figure out how we could detect issues with the binary expressions. Notably, these expressions here, left greater than right, left greater than equal to right, and all the other relational operators. These operators can detect and return an error, and we return an arithmetic error if they fail. And that's done in here, where we say, okay, for subtraction, you need a number and a number in order to do the subtraction. Otherwise, we're going to return an arithmetic error. For the comparison, we implement this partial ORD. And partial ORD can only return an option ordering. And the option ordering says less, greater, or equals. And those are your only three values you can put in ordering. Option obviously gives you an extra one called none. But if we return none, it makes the result of the expression false. So if we say nil is greater than true, we can return none from partial ORD, but this just makes the expression false. And so it seems like, nil is greater than false and nil is less than false. This would also return false. And that's less than ideal. The right way to do it would be to detect the error in comparison and report it. So I think we have to bite the bullet, and instead of doing instead of operator overloading, which is what we did here for add, multiply, divide, and subtract and comparison, instead of doing the operator overloading, we'll actually have to do the work in here, which I think will end up meaning duplicate code. Let's see how this plays out, right? Because what we can do is essentially, take a look at the object code, and what we do, for division, for example, we just destructure the two sides into left and right, and then divide, right? And we do for subtraction too, and for addition is handled slightly differently, because you can add two numbers, or you can use the plus operator to concatenate two strings. So we can match on that. We can say, instead of let result is on match on the operator, we can say result is match on left right. And if we end up with essentially what we have in here, we can just do this right here and say, okay, well, we're gonna do this operation, but we don't know what operation it is, and that's where we have to come up with the next level match. All right, so this just converts to a match of the token type, and then we can say left right, but then we have to convert it back into an object. So I think this is the way we have to go with this, which is unfortunate, because it means that we can do it for numbers, and then we'll have to do it for strings separately, and then we have to handle these special cases with equality, which we're aware. Up here somewhere, we had some special equality, rules that we have to follow. So let's do that, and then we'll dive into section 7.4, which is hooking up the interpreter. So I can do this. So this matches left right. It destructures it into a left right. So we can get this left right, and I think we can just say object num here. And then close, 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 close. And these, I think, all just stay the same. Right? And then any other operation is, I guess we can just leave this here. Right? So this means that now we can handle all the numbers, but we can't handle anything else. So everything else, let's see, yeah. So under there, so we can just say here, this is going to be a to-do for now. Oops. And I think, right, so this builds. I don't like the way this is hanging out here so long. But I think that our tests are going to fail now because our string tests won't work. Yeah, so we have not implemented yet for these guys. Nil equals nil. And it's coming through this oops condition here. Okay, so now we can handle it for strings, right? This is what I meant by code duplication. Now, if we do grab this line, put it here, and then just change these to strings. Now we can do plus for strings, which is going to be a little different, right? It's going to be stir format, left and right. And then we'll have bang equal and equals your strings. And I think everything else is going to be an illegal expression, which means we'll just return object arithmetic error. Maybe arithmetic error was the wrong name for it. And that closes that match. Something went wrong. Oh, I forgot that second bracket on the format. There we go. So now if we run the tests, glad I wrote the tests. We still have a bunch of tests. We have 3 failing tests. And, right, arithmetic error for subtraction. So, right, because we're still doing the oops thing. So, yeah, maybe this just returns arithmetic error too. Checked. I'm just saying you don't have 2 numbers or 2 strings, so we're going to just fail. And run these tests. And we still have 2 failing tests. Nil equals nil, right? Okay, so this is where we have to handle these conditions. So we have to say object nil and object nil. We're going to make that true according to this rule here. So that results in an object bool true. And then if nil and anything else is going to be false, and actually we should write a test for that first, and then we return a equals b, and then so everything else is just going to be an arithmetic error. For equality, I guess if we should also handle booleans, right? You want to handle booleans, object, for equality anyway. Oh, yeah, we have to see, this is where we have to do the match expression operator type. All right, you know what we can do is we'll just grab it here. Let op equals expr operator token type. And we can just say match op here. So here we'll say match op. Yeah, so there's a bunch of duplicated code because of all this. Oh, this is always true if it's equals. So bang equal is going to be false, and equal is going to be true, right? Because we're just comparing a nil to a nil. and anything else is going to be an arithmetic error. Right? If it says nil plus nil, it's going to be a mistake. If we have an object nil on the left side and anything else on the right side, it's going to return false for equals. If we're comparing it to not equals, I guess that's going to be true. Right? Because bang equals just the opposite of that. And anything else is an arithmetic error. So you can't add or subtract or compare nil greater than or equal to or whatever. And then what's left? This one here, we're going to check if A equals B. So we already have two numbers, we have two strings, we have the nil condition. What else do we have? Z89 says, let's go. Welcome to the stream, Z89. Yeah, so we have num, string, bool, and nil. So I think we've handled all the... Oh, we want to handle the Boolean cases too, right? So that's basically the string cases except with Booleans. So let's just copy and paste these guys. We can't plus them, but we can compare them equal to or not equal to each other. I think that covers everything. And like I said, I should have written test first for all this, but okay. The other thing I wanted to write test for was, well, let's see if it runs. Let's see. Did I get it all right? I still found something. Test for arithmetic error for greater. So we should be getting an arithmetic error. Oh, that's right. I changed this to is okay because we couldn't detect it then. So now it should be an error. Perfect. Okay. Right. So what was happening, we were comparing is 15 greater than true, and we should be returning an error. And we did, which is good. So the only other thing that's missing from our tests is handling all these code paths here. We're testing a couple of the graders, but not all of them. And it'd be good to test all of these guys. So I can write a little test runner and give it an operation and then a result list, maybe. Let's see if this works. Function run comparison test, I guess, and then it's going to take in a vec of tokens, a vec of tuples, ops, or compares. It's going to be a vec of tuples. It's going to have a token, and then what that token should result in on comparing two numbers. And it'll assert. So here's what I'm thinking is we'll just create 3 binary exprs. One where the first number is less than so 14. One where the first number is equal to, and one where the first number is greater than, so 16. And then each one should be able to run the binary expression. I'm just using shadowing in order to avoid having to retype a bunch of code. Right, and then so then we should be able to say these two things. And we're going to loop over, boom, 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 and then we'll loop over the comparisons for C in comps. Do that like that. And instead of saying true, 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 we're going to just say what should it be, right? So C.0 is going to be the token, which is going to be this guy here. And C.1 is going to be the result. So this will run the comparison test for 3 different compares. So I should be able to run now a greater than or equal to, oh, we don't need to do it this way. We can just say a vec of bools. Because we're going to use the same token each time. What was I thinking? Oops. Talk is token. Oh, I have to pass the token in because I think this needs the token directly, which might present problems now that I think about it. Right, so for example, now we can say test greater. No, let's test less than, because I don't think I have a test less. No, I don't. So test less than. And so now what we can do is say run comparison test for a less than token, which I'll just copy paste here. Less. That's less. So that's the token, comma, and then we create a vec of, and then we say, is this less than? Yes, true. And is this less than? No, it's false. And is this less than? No, it's false. And that should do all the correct asserts. I don't know if this is going to compile because the token might not be able to be moved. Oops, I got that bang in the wrong place. Okay, so that worked. Let's see if test less than runs. Oh, right. I have to change these now. The C.0. Oops. Should be a toke. And the C.1 is just a bool. Expected bool found bool. Okay, so we have to do that and stop hitting F1. Oh, value used here after move. Yeah, so, okay, so we have to say dupe. And that way we can actually pass in a reference. We don't have to pass. Ah, knock it off. Jeez. Okay. Okay, so test less than failed. Oh, and now we don't know. Okay, we do know which line it failed on. Okay, so 246 is where it failed. So 15 was supposed to be not less than 15. The left side was false. And we were expecting true? Oh, I see why. Because I'm an idiot. That's why. Because I'm an idiot. Okay, so we're going to say let nums equals vec 14.0, 15.0, 16.0. And we're going to always compare it against 16. And then this will just be C, nums C. Oh, that's not going to work, right? We have to zip it. And I don't know how to zip things. Nums C in compares dot zip nums. I don't know how to do this. And then, so we'll figure it out. Nums and C. And then this goes away. And how does this fail? Oh, we have to do iter zip. Oh, it's backwards. Okay. Oh, okay, that worked. Yeah, so the only thing is that we don't know which operation we're which one failed, right? So if this fails, okay, let's make it fail. If I change this to change less to be less than or equal to, the second one should fail, and we need to be able to figure out which one is failing. All it's saying is we got a true and we're expecting a false. But we don't know which one we were doing. Does Rust assert allow you to add text? As an optional. Yes, okay. So we can just put in extra text here. So assert EQ. Oh, this is the wrong one. Where is it? 4. There we are. Jeez. Okay. So what we're going to do is we're going to say testing something is something 15.0, and then that something is going to be nums, and the second something is going to be talk.lexeme, I think. Let's take a look. Yeah, just lexeme is the string that we're going to print out, and we might have to grab it as string. Yeah. All right, so if we do that and we run the tests, there. Testing 15 is less than 15.0. And it should have been true, and we got false. Okay, so now we can actually see it. That's good. So that way, now we can actually test all of them. Let's fix the less than bug here. And then, so then we should be able to do a test greater than or equal to. So test less than or equal to. And it should be basically just these 3 lines again. Except we're going to say less equal. And it's going to be false, true, false. And then we'll have greater than as a test. Just put that in buffer A, and then here we go. So this is greater than, and this is going to be false, false, true. Greater than or equal to. And greater than or equal to. And this should be true, and this should be false. Okay, we don't need this one anymore, right? And we don't need this one anymore. Okay, so now we're testing, I think we're testing all the conditions. Less, less equal, greater, greater, equal. And those match the actual operators that we're going to print out. Let's run the tests. And they all pass. Okay, that's good news. We can also do the same thing for this guy. We can do equals, and it should be false, true, false. And then we should be able to do a test not equals. And that should be the opposite. True, false, true. Oops. What did I do? Oh, there's another not equals. Okay, so we can get rid of this one. Oh, but yeah, so this is a test equals for numbers. And a test not equal for numbers. So we have to add all the other little corner test cases for nils and booleans and things like that. Because here's test equals nil. Test equals string. We need to test equals boolean. All right, I'm not going to get into all of that. I'm going to declare those as nice to have, but not critical for doing right now. So we got this all refactored, which is great. It only took a half hour. Oh, we can also remove, very sad, but we can remove now all of our standard ops stuff. Oh, damn it. Okay. Keep doing that instead of hitting test. All right, so everything builds, everything still checks, everybody's happy. Let's commit these changes. Git add source, git commit refactored binary expressions to remove operator overloading. Yeah, very sad because the operator overloading thing made it really nice. But now, okay, so now we're going to hook up the interpreter. Here we go. The visit methods are sort of the guts of the interpreter class, where the real work happens. We need to wrap a skin around them. Yeah, okay. To interface with the rest of the program. The interpreter's public API is simply one method. So interpret just calls evaluate and then prints it out. This takes a syntax tree for an expression and evaluates it. If that succeeds, evaluate returns an object for the result value. Interpret converts that to a string and shows it to the user. To convert a locked value to a string, we rely on this. Okay. This I don't think we need because we're already converting it to a string. But we can write the interpreter code. Oops, that's the test. Right here. So we can say pub fun interpret and give it an expression. And it's going to either, so we can say match self-evaluate expr. And it's either going to be OK, which returns a value, which means we can print on it. Or it's an error, E, which means, I guess we report it, call it e-report. And that's all we do. And that's essentially this println or the runtime error. Doesn't like that. Why doesn't it like that? Oh, because I mistyped evaluate. Oh. Yeah, so this just, okay, we still don't understand the location thing. Okay. So that's that. We have a new warning now because we're not using it. So this is calling stringify, but we don't need to do that because we already have that code in our object class. We have this display code. And it looks like what they're doing is stripping out, if it ends in .0, we just strip out the .0. That's what I'm reading here. I honestly don't know how Rust handles it, but we'll take a look. We can strip off the .0s if we need to, if it looks like that's what's happening. This is another of those pieces of code like isTruthy that crosses the membrane between the user's view of locks objects and their internal representation in Java. It's pretty straightforward. Since locks is designed to be familiar to someone coming from Java, things like booleans look the same in both languages. The two edge cases are nil, which we represent using Java's null, and numbers. Locks uses double precision numbers, even for integer values. In that case, they should print without a decimal point, right? So we're going to take a look at that. Since Java has both floating point and integer, it wants you to know which one you're using. It tells you by adding explicit .0. We don't care about that, so we hack it off at the end. Yet again, we take care of this edge case with numbers to ensure that JLocks and CLocks work the same. Handling weird corners of the language like this will drive you crazy, but is an important part of the job. Users rely on these details either deliberately or inadvertently, and if their implementations aren't consistent, their program will break when they run it on different interpreters. Yeah, so that's what I was talking about yesterday, is there should be nice if there were some sort of a locks validation suite that we could run once we're all done. Each chapter maybe would have been nice to have each chapter have a little validation suite you could download, run your code, and see if it does what you're expecting. Oh, nice to have. Okay, so reporting runtime errors. If a runtime error is thrown while evaluating expression, interpret catches it. This lets us report the error to the user and then gracefully continue. All of our existing error reporting code lives in the locks class, so we put that method there too. Okay, we don't have a locks class, but I do have this report function in the error code, so I think we're good. Well, we'll see. We use the token associated with the runtime error to tell the user what line of code was executing when the error occurred. Even better would be to give the user an entire call stack to show how they got to be executing that code, but we don't have function calls yet, so I guess we don't have to worry about it. After showing the error, runtime error sets the field, has runtime error. So I guess we can have interpret return that, right? Right, it could just return success or failure. So we could just do this and semicolon true, true for success, and maybe false for failure. Like that. I don't know, that looks a little ugly, but I think it'll do the trick. If the user is running a lock script from a file and a runtime error occurs, we set an exit code when the process quits to let the calling process know. Not everyone cares about shell etiquette, but we do. Okay. If the user is running a REPL, we don't care about tracking runtime errors. After they are reported, we simply loop around and let them input new code and keep going. All right, so running the interpreter. Now that we have an interpreter, the locks class can start using it. So we don't have a locks class, but we do have a main that calls the interpreter. Where do we call the interpreter? Oh, we don't call the interpreter yet. That's right. So we have an interpreter here. Should we create a locks class and then have these run file and run prompt and run functions in it? Would that be the way to go? And then here we would have the locks class and call locks.runPrompt, locks.runFile. Why not? Let's give that a try. So we do have an interpreter. We do have these errors that we're kind of ignoring because we're doing it a different way. We're doing it a rusty way, a sort of rusty way. Struct locks. So all these guys then, that's a pub fun, that's a pub fun, and that's a regular fun. This last one's a regular fun, right? And then we can close it this way, and then here we can just say let locks equals locks, and then say, oh, we don't have to do that. Oh, maybe we do. Let's see, locks dot. Oops. like that, and then this will take a self, because the locks, oh, what am I doing? This is impl. Impl locks. Struct locks contains the interpreter. So this needs a locks new. And then we'll need a pub fun new interpreter. No, locks returns a locks interpreter. Interpreter. Like that. I'm putting in mut self because I'm assuming we're going to need that. And then this is locks dot run buff. And then this is locks dot run line. And then this will just be, this will be mut self. And then instead of I think this is right after we parse, right? So instead of parse, instead of AST printer, I guess we can get rid of AST printer now. I'll comment it out. We can just say locks.interpreter.interpret expr. Okay, let's see what we blew up. 5 errors. Oh, right, we don't have the interpreter. Oh, self. Oops. Self run. Okay. Self. All right. But I don't think, yeah, I don't think it needs to be mutable yet. Why was I thinking it needed to be mutable? It feels like we're changing some state somewhere. I think that's what the fourth warning is all about. Is that we've got mutable when we don't need mutable. All right, well, let's see. Let's see what happens if we do this. No, we still have 4 ones. Okay, cargo check. All right, we're not using AST printer anymore. Let's just comment these out for now. Synchronize is still not being used, and yeah, the print function inside AST printer is not used, but that's okay. Oops. Oh. What am I doing? Okay, so now we're down to 2 warnings, and that's still the synchronized warning. So can we run this? We have a prompt, 3 plus 4. Huh, it worked. Oh, and it does not have the .o. That's amazing. So 3 plus 4 times 5. 23, that's correct. 3 times 4 plus 5. 17. 3 times 4 plus 5. 27. Wow. It's all working. I'm in shock. We now have a live parser. We have an entire language pipeline now, scanning, parsing, and execution. Congratulations, you now have your very own arithmetic calculator. As you can see, the interpreter is pretty bare bones, but the interpreter class and the visitor pattern we've set up today form a skeleton that later chapters will stuff full of interesting guts, variables, functions, etc. Right now, the interpreter doesn't do very much, but it's alive. Allowing comparisons on type. So these are the challenges. Let's get these changes committed, because we didn't actually do too much, right? Supercuber is back. Hi, Supercuber. We just hooked up the interpreter to the parser, and we created this new locks class, and we got things to run. Cargo run 42 times 78 is 3,276. So that's all working. Git add source, git commit section 7. I think it's 7.4. Yeah, so I can for interpreter. Done. Wow. All right, so the challenges are allowing comparisons on types other than numbers. Is 3 less than pancake? No, but it could be handled to enable things like ordered collections on heterogeneous types, or it could simply lead to bugs and confusion. It might be nice to have string compared to string. Many languages define plus such that if either operand is a string, the other is converted to a string. Yeah, we can do that. Extend the code and visit binary export to support that. Yeah, we can do that. Why don't we do that now? And then what happens right now if you divide a number by 0? That's a great question. Let's do it. Inf. We get inf. What do you think should happen? Justify your choice. How do other languages you know handle division by 0, and why do they make choices they do? This must be something Rust is doing for us, right? Because what we have in our interpreter is we just take the number divided by the other number and make it a number, an object number, and it becomes inf. And when we display it, how does that get displayed? All we're doing is saying write it. And it turns out to be inf. Supercuber says try dividing by -0. Negative inf. Supercuber says this is actually just floats doubles behavior. I thought it would have been like not a number, man. But I guess Rust does inf instead. Well, we can do this one. This one seems like it's pretty straightforward. So why don't we try that before we give up on this chapter completely? So that means we're going to have to play around here. We're going to add one where we have a number on one side and a string on the other, and one where we have a string on one side and a number on the other. And it's just this, right? Otherwise this. It's the same exact code. A lot of code duplication, unfortunately. Cargo run. 3 plus 4. 3, 4. 3 plus 4. 3, 4. Okay, so that works. Do we want the quotes here? I don't think we want the quotes here because we're just printing out a string. Oh yeah, I'm deliberately putting those quotes there. Okay. Good enough. Let's fix that. Cargo, oh no, git add that. Git commit. Don't print double quotes around strings. And we just have this git add source, git commit. And this is going to be concatenation works for mixed numbers and strings. And if we wanted to add it for booleans and nil, we'd have to extend it even further than that, which is a little frustrating, but there you go. Design note, static and dynamic typing. Some languages like Java are statically typed, which means type errors are detected and reported at compile time, right? Others like locks are dynamically typed and defer checking for type errors until runtime right before an operation is attempted. We tend to consider this a black and white choice, but there are actually a continuum between them. Turns out even most statically typed languages do some type checks at runtime. The type system checks most type rules statically. The type system checks most type rules statically, but inserts runtime checks in the generated code for other operations. For example, in Java, the static type system assumes the cast expression will always safely succeed. After you cast some value, you can statically treat it as the destination type and not get any compile errors, but downcasts can fail, obviously. The only reason the static checker can presume that casts always succeed without violating the language's soundness guarantees is because the cast is checked at runtime and throws an exception on failure. A more subtle example is covariant arrays in Java and C#. The static subtyping rules for arrays allow operations that are not sound. This code compiles without any errors. The first line upcasts the integer array and stores it in a variable of type object array. The second line stores a string in one of its cells. Object array type statically allows that. Strings are objects, but the actual integer array that stuff refers to at runtime should never have a string in it. To avoid that catastrophe, when you store a value in an array, the JVM does a runtime check to make sure it's an allowed type. If not, it throws an array store exception. Oh, that's a new one on me. Interesting. Java could have avoided the need to check this at runtime by disallowing the cast on the first line. It could make arrays invariant, such that an array of integers is not an array of objects. That's statically sound, but it prohibits common and safe patterns of code that only read from arrays. Covariance is safe if you never write to the array. James Gosling and the other Java designers traded off a little static safety and performance in return for some flexibility. Even Haskell will let you run code with non-exhaustive matches if you find yourself designing a statically typed language. Keep in mind you can sometimes give users more flexibility without sacrificing too many of the benefits of static safety. Okay. All right, so I think we're done with Chapter 7, Evaluating Expressions. I'm trying to think if there's anything else I wanted to do. Oh, there was something. Unfortunately, maybe I'll save that for tomorrow morning. If I do a cargo clippy, there's a billion and 6 errors here, which I want to address. And most of it is in my code generating code, my metacode. I should be using writeLin instead of write. I don't know why I ended up doing that. Write instead of writelins. But that's the majority of them. And then there's a couple of little things about using vex and things. I looked at that yesterday, so tomorrow morning maybe we'll dig into that first, and then we'll go into the actual code. So we're done here. Let's go to statements and state. All right, the interpreter we have so far feels less like programming a real language and more like punching buttons on a calculator. Shiloh, hey, welcome to the stream. Programming to me means building up a system out of smaller pieces. We can't do that yet because we have no way to bind a name to some data or function. We can't compose software without a way to refer to the pieces. To support bindings, our interpreter needs an internal state. When you define a variable at the beginning of a program and use it at the end, the interpreter has to hold on to the value of that variable in the meantime. So this chapter, we will give our interpreter a brain that cannot just process but remember. You could make a language that treats variable declarations as expressions that both create a binding and produce a value. The only language I know that does this is Tickle. Scheme seems like a contender, but note that after a let expression is evaluated, the variable it bound is forgotten. The defined syntax is not an expression. Yeah, I can't think of any language that use variable declarations as expressions. Supercuber says you end up making the code generation. I don't think I ended up needing it. I'm not sure what you mean by the code generation. Charlotte says, what are you going to name the language? This language is already named. The name is LOX. And it's a language that's designed by this book. Supercuber says, maybe because I skipped the visitor pattern and just made methods without the trait. Oh, the code that writes code. Yeah, so I did end up doing that. I've got this generate AST. Miser wrote, and I probably don't have it anymore. Yeah, it's still here. Mizzard wrote this macro, which does what this is doing. Although this has been tweaked a little bit since Mizzard wrote this. But it basically is just a macro, so you write this, and this takes the place of all of this code, which is really, really neat. And this, I think, is the right way to go with Rust for this kind of thing, if you're not going to just write it by hand. And I think writing it by hand is a perfectly acceptable way to go. I was just following the book, so. Okay, statements. State and statements go hand in hand. Since statements by definition don't evaluate to a value, they need to do something else to be useful. That something is called a side effect. It could mean producing user visible output or modifying some state in the interpreter that can be detected later. The latter, modifying some state, makes them a great fit for defining variables or other named entities. In this chapter, we'll do all of that. We'll define statements that produce output and create state. Shiloh says, this is your version of it, so I think you can name it. Okay, well, I'm naming it locks AST. That's my name for it. And then finally, we'll add blocks and local scope. That's a lot of stuff. That's a lot to stuff into one chapter, but we'll chew through it all, one bite at a time. All right, statements. We'll start by extending Locke's grammar with statements. They aren't very different from expressions. We'll start with the two simplest kind. An expression statement lets you place an expression where a statement is expected. They exist to evaluate expressions that have side effects. You may not notice them, but use them all the time in C, Java, and other languages. Anytime you see a function or method call followed by a semicolon, you're looking at an expression statement. Pascal is an outlier. It distinguishes between procedures and functions. Functions return values, but procedures cannot. There's a statement form for calling a procedure, but functions can only be called where an expression is expected. There are no expression statements in Pascal. I remember playing with Pascal a long time ago, and I remember it being very verbose syntactically, because everything was begin-end instead of open brace and close brace. But I don't remember too much more than that. Okay, a print statement. Supercuber says rlocks is already taken by me. Yeah, okay. You beat me to rlocks. Maybe I can call this Uncle Locks. Uncle Locks. That looks really bad. Okay, the print statement evaluates an expression and displays the result to the user. I admit it's weird to bake printing right into the language instead of making a library function. Doing so is a concession to the fact that we're building this interpreter one chapter at a time and want to be able to play with it before it's all done. To make print a library function, we'd have to wait until we had all the machinery for defining and calling functions before we could witness any side effects. So, yeah, Python went through this pain point as well, right? Python 2, the print statement is a built-in, whereas Python 3, it's promoted to be a real live function, and that was a breaking change. But yeah, you know, this is a toy language for learning, so I'm not worried. When I say toy language, I mean it seems like it's going to be a very fully featured language which teaches a lot of stuff, so I don't mean to disparage it by calling it toy. I will note with only a modicum of defensiveness that BASIC and Python have dedicated print statements, and they are really... Oh, yeah. Granted, yeah, I should have read this first before I started blathering on about Python. Yeah, 3.0 removed the print statement, and now it's just a regular function. Okay, new syntax means new grammar rules. In this chapter, we finally gain the ability to parse an entire LOX script. Since LOX is an imperative, dynamically typed language, the top level of a script is simply a list of statements. So these are the new rules that we have to handle. Right, the first rule is now program. So it used to be expression, right? We started with expression. Let's take a look at our parser real quick here. When we call parser parse, we call expression right now. But I guess we're going to be calling statement or program. First rule is now program, which is the starting point for the grammar and represents a complete lock script or REPL entry. Program is a list of statements followed by a special end of file token. The mandatory end token ensures the parser consumes the entire input and doesn't silently ignore erroneous unconsumed tokens at the end of a script. Right. So if it parses all the way and it gets to something which causes it to stop, if you don't have this EOF thing, it could stop before the end, and then a user of your program, of your interpreted language, might not know that the entire thing wasn't working, and there would be a lot of angry debugging sessions. Right now, statement only has two cases for the two kinds of statements we've described. We'll fill in more later in this chapter and in the following ones. The next step is turning this grammar into something we can store in memory. Syntax trees. Aren't we already doing syntax trees? As a result of this parsing? Right, we're creating all these expers. Oh, okay, so maybe they're just saying, okay, we're going to turn this grammar for statements into syntax trees, just like we turned the grammar for expressions into syntax trees. Got it. There's no place in the grammar where both an expression and a statement are allowed. The operands of, say, plus are always expressions, never statements. The body of a while loop is always a statement. Since the two syntaxes are disjoint, we don't need a single base class that they all inherit from. Splitting expressions and statements into a separate class hierarchies enables the Java compiler to help us find dumb mistakes, like passing a statement to a Java method that expects an expression. That means a new base class for statements. As our elders did before us, we will use the cryptic name statement. With great foresight, I have designed our little AST metaprogramming script in anticipation of this. That's why we passed in expr as a parameter. Now we'll add another call to define statement and its subclasses. Not really foresight, I read all the code for the book before I sliced it into chapters. The generated code for the new nodes is here. Oh, I see. So they're showing you what the code should look like. Charlotte says, what window manager are you using? I am on a Mac, so I'm using whatever is built into the Mac. That's my window manager. I don't know if it has a name. All right, so we're going to create this new AST. Let's make sure. Are we clean? We are clean. Okay. So I should be able to, actually, since while I'm in here, I should clean up all those rights. So this is the define AST for expr. We should be able to just define AST here, output dir statement, right? And then to string, and what do we have? Back bang. And this is going to be expression. And then a print. Let's put a space there. So we have in the other one, expr expression. And that closes that closes that, and that closes that. If I run this, is this going to fail? Something different like it. What did I do wrong? Oh, I have to two-string these guys. I should clean that up too. I shouldn't have to do a two-string. Okay, so that worked. We should now have a statement. Okay, so this just got generated by our code. This is a brand new file. I mean, it looks okay. I don't know. So run the AST generator script and behold the resulting statement Java file with the syntax tree classes we need for expression and print statements. There we go. Don't forget to add the file to your IDE project or makefile or whatever. Okay, right. I got to add it to main. Right, we have mod expr, we have mod statement. Are we going to just get rid of AST printer? We don't need it anymore, right? I don't know. I'm going to leave it for now in case it comes in handy for debugging. Okay, I just tried to save that and we already have a failure. Statement visitor not found in this scope. Oh, because I hard-coded expr. Oops. I didn't even notice that before. Edit, generic. There we go. So somewhere I have expr here. Yeah, so this should be this. And then this should be base name. Okay, so we still have two errors. Oh, expr is not found. Yeah, we have to add that up here. Oh, that's going to be a problem because Rust doesn't like it when you do that. If I just add it by default like this, Rust is now going to complain that expr has a problem because you can't glob import a module onto itself, into itself. Supercuber says put star locks into get info exclude. when I was reading that, I thought you were gonna say git ignore. I'm not familiar with git info exclude. Huh. Okay, that's a new one on me. Thank you for teaching me that. Is that cleaner now? That's cleaner now. Yeah, I've just been ignoring this the whole time, right? And I'm sure it's been bugging everybody. All right, so this doesn't build because now we need to be able to figure out I wonder if we should just have another vector here of includes. Superkeeper says git info exclude is for files that only apply to you and not to other people who might use this. I see. But so it doesn't get added to the repo. I got it. Okay. Do I like using IETA? I don't know what IETA is. Could you clarify? What am I doing here? So, all right, I was going to try to add maybe I can make a list of all these guys. Maybe make a new vec. And maybe I'll make them strs this time. Error, token, and object. And then the same here, except this will include expr. And then we can say imports. Do I like using idea? I'm still not following. What's idea? Oh, IntelliJ maybe? Is that what you're saying? I don't use this IntelliJ idea. I don't use that. I don't even use it in my day job. JetBrains. Yeah. So I don't know. I don't have any familiarity with that. Sorry about that. So now I can say for I in imports, I can say writeLin, file, use crate, split, star, semicolon, and give it I. Will that do the trick? Didn't like something. Oh, I forgot to bang. There we go. And that's not an iterator, but that is. There we go. Okay. So built, we now have 12 warnings instead of whatever. But now our statement now includes expr, and our expr does not include expr. So I think we solved that problem. Right. So okay. So we've added these lines here. We now can generate expressions and prints. Cargo check. And the errors are, oh, there's a whole bunch of stuff we're not using. Duh. Okay. So the parser's parse method that parses and returns a single expression was a temporary hack to get the last chapter up and running. Now that our grammar has the correct starting rule program, we can turn parse into the real deal. Oh, so now it needs to return a vector of statements. So instead of returning an option expr, this needs to return a vec of statement, which means we need statement here. And that's going to cause our locks code to break. Okay, well, it's going to cause a lot of things to break, apparently. Okay, so we'll create a new let mut statements is vec new. And then while not self is at end statements dot push self statement. Oh, this needs to be result. because I want to put a question mark there. And then we can just return statements. Oh, and we haven't written any of the other stuff. Okay. What about the code we had in there for catching parse error exceptions? We'll put a better parse error handling in place soon when we add support for additional statement types. Fair enough. Well, we're going to return it anyway, so I'm good. This parses a series of statements, as many as it can find, until it hits the end of the input. This is a pretty direct translation of the program rule into recursive descent style. We must also chant a minor prayer to the Java verbosity gods since we are using array list now. Okay, so Vec is in Prelude, we don't have to do that. A program is a list of statements, and we parse one of those statements using this method. Okay? This is an add after expression. Does it really matter where it goes? I guess I'll put it where they say to. Maybe we'll come back to it later. Oh, now we're going to return a statement. So this returns an expr. So this returns a statement. Right? I'm going to say if self is match. What they called it? Yeah, is match, and I'm going to give it this token type print. Then we're going to return self print statement question mark. Oh no, we can just return the whole thing, right? Because if that returns a failure or a locks error, it could just returns. That's fine. Otherwise, we're going to return self expression statement, which is going to be different to just an expression. Okay, a little bare bones, but we'll fill it in with more statement types later. We determine which specific statement rule is matched by looking at the current token. So a print token means it's obviously a print statement. If the next token doesn't look like any known kind of statement, we assume it must be an expression statement. That's a typical final fall-through case when parsing a statement, since it's hard to proactively recognize an expression from its first token. Each statement kind gets its own method. So first print. So this is saying add it after statement. And this is also going to return a result of statement or locks error. We're going to say let value equals self expression question mark consume. We already wrote that, right? Yeah, that's over here. Okay, consume token type semicolon expect semicolon after value question mark, and then return. Oh, and it's okay statement colon print statement. I think I haven't looked at this yet. Well, not in detail. Yeah, print statement is just has an expression. Okay, so print statement has expression of value, and value is going to be an expr. Can I just do that, or is that going to fail because I can't move it? We'll find out. And then we have expression statement. Yeah, since we already matched and consumed the print token itself, we don't need to do that here. We parse the subsequent expression, consume the terminating semicolon, and emit the syntax tree. If we didn't match a print statement, we must have one of these, which is the expression statement. And this result is a statement or a locks error. We do let expr equals self expression. We consume a semicolon. And then we would create, so it's almost exactly the same code, except here, instead of making a print statement, we're making an expression statement. And it blew up. Value is now, oh, expr, right. Expr, okay. 5 errors. Oh, this is an okay of statements. Got it. And what is this? Expected result found. Oh, because I put a semicolon there. Okay. Oh, did I typo expression? E-X-P-R-E-S-S-I-O-N. I did. Look at that. E-X-P-R-E-S-S-I-O-N. That's the next error. Oh, yeah. So we have an issue here now. Parser parses returning a list of statements to interpret. So we're going to have to deal with that. Yeah. Okay. So does everything else build though? Yeah. Okay. So everything else is compiling. So we're going to have to go to executing statements. Right. Similar to the previous method, we parse an expression followed by a semicolon. We wrap that expert in a statement of the right type and return it. So now we're up to executing statements. All right. So we're running through the previous couple of chapters in microcosm, working our way through the front end. Okay. Not sure what he's getting at there. Our parser can now produce a statement syntax trees. Our parser can now produce statement syntax trees, so the next and final step is to interpret them. As in expressions, we use the visitor pattern, but we have a new visitor interface, statement.visitor. In our case, it's just the statement visitor without the dot in between. To implement, since statements have their own base class, we add that to our list of interfaces interpreter implements. Java doesn't let you use lowercase void as a generic type argument for obscure reasons having to do with type erasure and the stack. Instead, there's a separate capital void type specifically for this use, sort of a boxed void like integer is for int. So what does that mean for us? I guess we could just use unit. Statement visitor. Can we do that for interpreter? Let's see if that. Oh, we have to include. Yeah, so we're missing these, but it's not complaining about the fact that I used unit. So I guess unit's acceptable instead of the void here. Unlike expressions, statements produce no values. So the return type of the visit method is void, not object. We have two statement types, and we need a visit method for each. The easiest is expression statements. So this thing, put it after evaluate, but I can't put it after evaluate because evaluate is inside the main impl part. So I just have to do it the rusty way and put it in here. Visit expression statement. Self and statement. And this would be, I guess, expression statement. The result is going to be unit or locks error. And what are we putting in here? Just evaluate. So just self-evaluate. Statement.expression. And I guess we have to ampersand it. And then it says return null. What does this return? This returns an object. So we could just put a question mark here, right, to return the locks error if one is generated, and then just say OK. Is that the way to do this? We evaluate the inner expression using our existing evaluate method and discard the value. Yeah, OK. Then we return null. Java requires that to satisfy the special capitalized void return type. Weird, but what can you do? Appropriately enough, we discard the value returned by evaluate by placing that call inside a Java expression statement. Okay. I think it just means that this just compiles and throws away the return code. So, all right. The print statements visit method isn't much different. Okay. But now we're going to actually save the value and print it. Okay. So let value equals self-evaluate, statement expression, question mark. And then we can just say println, bang, value. And then return null, which is, in our case, okay. Before discarding the expression's value, we convert it to a string using the stringify method we introduced in the last chapter, and then dump it to standard out. And that all checks. So all we have now left to do is this. So our interpreter is able to visit statements now, but we have some work to do to feed them to it. First, modify the old interpret method in the interpreter class to accept a list of statements, in other words, a program. Okay. So interpret. So instead of expression, we're going to just take a list of statements, which is going to be stmt, and this is going to be stmt, like that. And instead of this, we're going to say for, I guess we call it statements. Let's just follow their variable names here. Statement and statements. And the way we're going to just do this, I guess, is going to try this. This is reporting the error, but not returning it. I guess. So what do we do for this case here? Do we just say continue and then break? Oops, I use a semi and then break here. And we can just say let mod had error is false. Had error is true. And just return had error. I don't know. Does this seem reasonable to you guys? Oh, except we don't have that. We have statement. Oh, it's called execute now. Execute. I missed that. Okay, so we're going to do an execute on a statement. And now we have to write execute, which is just statement accept. Okay. This replaces the old code which took a single expression. The new code relies on this tiny helper method called execute. Fn execute self statement, which results in either nothing or a locks error. Right? Because that's what statements do. Statement accept this self. Okay. That's a statement analog to the evaluate method we have for expressions. Since we're working with lists now, we need to let Java know. No, we don't. Well, we don't need to let Rust know. The main locks class is still trying to parse a single expression and pass it to the interpreter. Right, so we're going to have to fix that. So main. That's over here. So now we just grab let so parser parse now returns this list, right? Like that. And then replace the call to interpreter with this. Okay, so we can just say self interpreter interpret statements. And then we'll figure out what happens after that. I guess this can get a question mark, right? Oh, we don't need to do that. We can just return the result of that. What's wrong with this? Doesn't like this. Cannot be formatted with the default identifier. Display is not implemented for unit. Oh, right. We don't need to print these out anymore. So we can just say if self-execute statement is error. Oh, no, that's right. We still want to match because we want to deconstruct it. We want the error. Oh yeah, so we can say if let error E is equal to that, then e.report and break. Okay. And this is this, and there's no more error. We don't return an error anymore, right? Because interpret returns a bool if it worked, or a true if it worked, or a false if there was an error along the way. So this is going to change to bool. And then we're going to deal with it up here. Locks.run, or self.run. We'll handle both of those cases here. Oh, here we're just ignoring it. And here, you don't have to check to see if it's an error. We can just say if not, and exit. I guess we should try to distinguish between runtime errors versus, because the different error codes mean different things. And that's something maybe we can do on our to-do text. Convert different error types, runtime, parsing, and I guess scanning into their own error codes. Command line. Right? Okay, and then we'll add that to our things to do. All right, but does this check? This does not check. What do we do wrong here? Oh, no more question mark there. Ah, right. So this does actually need to report back whether or not it's scanned. Okay. So let's leave it like that. This can still do an is error. And this can just be if this, then okay, else error, locks error, error, something, which I've forgotten what the API is already. Usize, 0 message, nothing. What a hack. Okay, and then this is expecting a statement, and it found a new result. Okay, so this needs a question mark. Found vec. And this doesn't like this because I put a semicolon there. There we go. We still have 6 mornings though. Oh, statement is not using token and object. So those we can clean up. And this I forgot the question mark on. Okay, so let's fix those. Line 46 needs a question mark. And statement does not need token or object. Just needs error and expression. Yeah, okay. So now I think we're back down to the synchronize issue. All right, so basically just plumbing in the new syntax. Okay, fire up the interpreter and give it a try. At this point, it's worth sketching out a little locks program and text file to run as a script. Okay. And we'll say print 1, print true, print 2 plus 1. Cargo, run first. Oh, we got an error. And this is the error saying that we returned false from... Oh, that was had error. I got the backwards. Okay, good. So I think it means it worked. Because this should be had... Oops. Had error. So bool true means there was an error. Which means I should say this. Maybe it should return success instead. And change this to false. That way it seems more natural. Say interpret. If interpret works, then we're good. cargo run first. All right, so we have 1 false and 3. That's wrong. 1 is correct, but I said print true and it printed false. So we have a bug. Wonderful. All right, I've got a half hour left. Let's track down this bug. Why are we getting false coming out of here? Is it maybe there's just a bug in our object printing code here? No, it says if X, write true, otherwise write false. Println debug mode. Self. Okay, cargo run first. Oops. Yeah, it is coming with bool false. So is that a bug in our token generation? This is where having the AST printer would have been handy, right? So let's link that back in. Source main. We can still scan. We can take all the tokens that we got and print those for T in tokens. T. So let's see what got scanned in. Print 1, print true. The literal. This is true. But it should have been a literal not. Oh, we're not translating the true into a literal. Whereas these are being converted to literals. This is a true. Is there? Did I miss some code somewhere which converts the true into a Boolean? Or maybe when I refactored things, I didn't refactor this properly. Yeah, so if this is alphanumeric, we add a number into our scanner, which generates this token type number. Okay, yeah, and what I was doing was converting it to, if you look here, it just converts it to a token type of true. Which means we're not seeing it as a Boolean. So in our parser, oh, well, I mean, that would explain it. Why is that saying false there? Okay. Oops. There we go. Okay. Let's unwind all of those changes now. We don't need this. And we don't need this little thing in here. Cargo run first. 1, 2, 3. Okay, and then get status. Get diff. Okay, so what I changed here, get diff source parser. Yeah, and then we fix this separately. Okay, get add source and generate AST. git add to do. So what did we do? We added, as this was section 8.1, git commit -m section 8.1, initial hooking up the interpreter. 516D, thank you for the follow. Okay. Global variables. Should we dive right in? I have a half hour left. I don't know how far I'll be able to get with this. Let's see. Now that we have statements, we can start working on state. Before we get into all of the complexity of lexical scoping, we'll start off with the easiest kind of variables, globals. We'll need two new constructs. Global state gets a bad rap. Sure, lots of global state, especially mutable state, makes it hard to maintain large programs. It's good software engineering to minimize how much you use, but when you're slapping together simple programming languages, or heck, even learning your first language, the flat simplicity of global variables helps. My first language is BASIC, and although I outgrew it, eventually it was nice I didn't have to wrap my head around scoping rules before I could make a computer do fun stuff. I mean, that's fair, right? A variable declaration statement brings a new variable into the world. This creates a new binding that associates a name with a value. Once that's done, a variable expression accesses that binding. When the identifier beverage is used as an expression, it looks up the value bound to the name and returns it. Later we'll add assignment and block scope, but this is enough to get moving. Okay, as before, we'll work through the implementation from front to back, starting with the syntax. Variable declarations are statements. Adelphos, thank you for the follow. And variable declarations are statements, but they are different from other statements, and we're going to split that statement grammar in two to handle them. That's because grammar restricts where some kinds of statements are allowed. The clauses in control flow statements, think the then and else branches of an if statement or the body of a while, are each a single statement, but that statement is not allowed to be one that declares a name. This is okay if Monday print already, but this is not if Monday var beverage equals espresso. We could allow the latter, but it's confusing. What is the scope of that beverage variable? Does it persist after the if statement? If so, what is its value on days other than Monday? Does the variable exist on all those days? Code like this is weird, so C, Java, and friends all disallow it. It's as if there are two levels of precedence for statements. Some places where a statement is allowed, like inside a block or at top level, allow any kind of statement, including declarations. Others allow only the higher precedence statements that don't declare names. In this analogy, block statements work sort of like parentheses do for expressions. Block itself is in the higher precedence level and can be used anywhere, like in clauses of an if statement, but statements it contains can be lower precedence. You're allowed to declare variables and other names inside the block. The curlies, I assume curly braces, right, let you escape back into full statement grammar from a place where only some statements are allowed. To accommodate the distinction, we add another rule for the kinds of statements that declare names. So we have a program makes a declaration. So that's the change, right? It used to be program was a list of statements. Now the program is a list of declarations, and declaration is a variable declaration or a statement. Declaration statements go under the new declaration rule. Right now it's only variables, but later it will include functions and classes. Any place where a declaration is allowed also allows non-declaring statements, so that the declaration rule falls through to statement. Obviously, you can declare stuff at the top level of a script, so a program routes to the new rule. The rule for declaring a variable looks like this: var identifier equals expression. Like most statements, it starts with a leading keyword, in this case var, an identifier token for the name of the variable being declared, followed by its optional initializer expression. Finally, we'll put a bow on it with a semicolon. To access a variable, we define a new kind of primary expression. Okay, so we're going to have to modify our primary code. That identifier clause matches a single identifier token, which is understood to be the name of the variable being accessed. These new grammar rules get their corresponding syntax trees. Over in the AST generator, we'll add a new statement node for variable declaration. And we have more generated code here. Okay, so we're going to do this. So instead here, we're going to add var, and it's going to contain a token name and expr initializer. Like that. It stores the name token so we know what it's declaring, along with the initializer expression. If there isn't an initializer, that field is null. Oh, that means this needs to be an option. Then we'll add an expression node for accessing a variable. Variable token. Oh, after unary. Oh, up here. Okay. Variable token name. It's simply a wrapper around the token for the variable name. That's it. As always, don't forget to run the AST generator script so you get updated expr and statement. Yeah, so if I run this now, it's going to complain in interpreter that we're not implementing. Cannot find token. Oh, right. We have to add token here. I took it out before, but now I have to add it back in. Yep. Okay, so statement visitor is missing visit var, and expr visitor is missing visit variable. Perfect. Parsing variables. Before we parse variable statements, we need to shift around some code to make room for the new declaration rule in the grammar. The top level of a program is now a list of declarations, so the entry point method to the parser changes. Okay. This is in function parse. Instead of this, we're going to just call it declaration, which we will have to write. It says add after expression. I don't know why it's always after expression, but it is. Declaration oneself results in, and this has to be a statement, right? Yes, it returns a statement right there. If self is match, open ampersand open token type var, then we're going to return self var declaration. Otherwise, we're going to return a, oh, here's where we're going to call synchronize finally. If it doesn't work, then we have to call synchronize. So we're going to call statement. These, okay. All right, so how are we going to do this? This is tricky because what happens is we can't just say return this because we want to catch the locks error and synchronize before we return a null. Oh, return null. So what we could do for now, and maybe this will break later, but we can say let result equal this else self statement, right? Take out the semicolon there and put the semicolon there. And then we can say if result is error, we want to call self synchronize. But we still return results because that gives us the error back. I think this is the best way to map it into Rust. So if either one of these returns an error, we're going to see that here. We're going to do the synchronize and then return the locks error. If either one of these works, we don't synchronize and we just return the resulting statement, which is going to be okay already because that's what these guys return as a result. So var declaration is going to need to do the same thing. I think this will work. Hey, do you remember way back in that earlier chapter when we put in the infrastructure in place to do error recovery? We're finally ready to hook that up. Yep, so that's there. So actually, if I do a save on this, oh, it's not going to work because we still don't have those guys, right? All right, one thing at a time. This declaration method is the method we call repeatedly when parsing a series of statements in a block or script. So it's the right place to synchronize when the parser goes into panic mode. The whole body of this method is wrapped in a try block to catch the exception thrown when the parser begins error recovery. This gets it back to trying to parse the beginning of the next statement or declaration. The real parsing happens inside the try block. First, it looks to see if we're at a variable declaration by looking for a leading var keyword. If not, it falls through to the existing statement method that parses print and expression statements. Oh yeah, so we already have statement somewhere. Yeah, right here. But we don't have var declaration yet. Remember how statement tries to parse an expression statement if no other statement matches? An expression reports a syntax error if it can't parse an expression at the current token. That chain of calls ensures we report an error if a valid declaration or statement isn't parsed. When the parser matches a var token, it branches to this. Okay, so let's do this. And it's saying put it after print statement. Okay, so we're going to say let name is equal to consume token type identifier. And then we're going to say let initializer. Oh. Let initializer. Okay, I think we can do this if self is match. Token type equal. Oh, assign. We called it assign. And then we call self expression sum. Self expression, right? Because the initializer is an option. Question mark in there, else none. That's the initializer, and then we're going to consume the semicolon. And then return, okay, statement, var. Like that, var statement, and then it has a name and an initializer. And I don't remember what they're called, so I'm just going to put it like that, and then let Rust tell me what they're supposed to be. Oh, self-consume. Self-consume. Var declaration, help there's an associated method with the same name. Oh, var declaration. That's it? That's it. Okay. So I guess they are called name and initializer. Perfect. We're good. Let me put a little blank line there because I like that. Okay. As always, the recursive descent code follows the grammar rule. The parser has already matched the var token, so next it requires and consumes an identifier. That's this guy here. An identifier token for the variable name. Then if it sees an equals token, it knows that there is an initializer expression and parses it. Otherwise, it leaves the initializer null. In our case, it's none. Finally, it consumes the required semicolon at the end of the statement. All of this gets wrapped in a statement var syntax tree node, and we're groovy. Parsing a variable expression is even easier. In primary, we look for an identifier token. All right, so let's find primary. It's right here. It's just before left paren. So which one is left paren? Down here. If self is match, token type, identifier, then we're going to return, okay, expr variable previous, and I don't know what it's going to be called, value maybe, just like that, and then we say self previous literal clone. Oh, expr variable, and I have to say variable expr. That's why. That's why my parentheses weren't matching up. Okay. Does that work? Nope, it's not called value. What's it called? Name. Available fields are name. Still doesn't like it. Expected struct token found enum option. Oh, so this should be self previous what? Just self previous? Because previous returns a token, right? So we're expecting a token. Still doesn't like that. Oh, expected token found found a reference. Okay, we might have an issue then. Right? Because how do we get... I mean, we're looking at this guy here. We did it with operator. So we should be able to do it with token, with variable expr. Oh, I called dupe on it. That's how I did it. Yeah, okay, that did it. Okay, very good. Clone doesn't work, but dupe does. Because I wrote dupe myself. Okay, so that's this code here. That gives us a working front end for declaring and using variables. All that's left is to feed it into the interpreter. Before we get to that, we need to talk about where variables live in memory. And we're going to talk about environments. And because it is now 10:09 a.m. my local Eastern time, I think I'm going to call it a stream. We don't have either one of these working yet. So let me get it at least so it compiles. Yep, and then for this one, what are we looking for? A variable expr visit. And it's going to be self expr variable expr result object locks error. And we're just going to say okay object nil. All right, so it builds. Cargo check. I guess we can turn those warnings off, right? Okay, we're clean. Git add source and generate AST. Git commit section 8.2 beginnings of variables. So it doesn't do anything, right? If I say cargo run, var a equals 3, print a, nil. Yeah, so it's just returning nil right now. And I don't know what this is doing for that statement either, so it's doing something. Oh, Brooke, how you doing? Brooke Zerker. I'm about to hop onto your stream. I know you're about to start streaming in about 10-15 minutes, so I will be lurking in that. But I'm really enjoying the book so far, to answer your question. I'm relearning a lot, and I'm learning new stuff as well. So this is good, and I'm also learning more Rust than I thought I would, which is also good. So let me get this all pushed. We're clean, right? And let's take a look over here. There we go. Okay, so we did a lot. We finished out section 7, chapter 7, and we started chapter 8. Hazemaker, thank you for the follow. Yeah, and then tomorrow we're going to start digging into environments. And I know Supercuber was warning me that environments and scoping are where things start to get murky and difficult. So I'm looking forward to that, I guess. Brookzerker says it sounds like a fun challenge. It is a lot of fun. A lot of fun. One of the things that makes it good for streaming, I guess, is that the design is already here. So I don't have to think about design. I can just write code. Whereas if I'm writing my own thing, I would have to spend time thinking about design on stream, which is a lot of, dead air. Dead air kind of stuff. So this is good for streaming. I like it. Okay, with that, I'm going to take off. I will hopefully see everyone tomorrow, and we can dig into environments. And then next week, we're going to get back to making a roguelike. But that's for next week. All right. Let's see. Thanks for hanging out, everyone. Hope you have a great rest of your day. Take care, and I will see you tomorrow.
So breaking here is not the right thing to do. And also, this is very verbose to do it this way, so we're not gonna keep doing this. Hello, scientist, how you going? Thank you for the raid. Welcome, raiders. How you all doing? Okay, so this is now doing all the parsing. This was the old parser stuff that we have here. It dealt with such wonderful whimsy, like white space characters and stuff.